Hi everyone, my name is Nick Thornburg, and I'm a PhD candidate in the Chemical and Biological Engineering Department. Today I'm going to be talking about some different tools for making industrial chemical processes more sustainable. Industrial chemicals are everywhere, whether or not we realize it. Everything from the household cleaners underneath your sink and the laundry detergent you use to clean your clothes, everything inside of our medicine chests, everything from the nylon inside of your rain jackets to the Nalgene bottled plastics that we use every day. Specifically for my research area, all of the foams inside of your furniture, the paints inside and outside of your homes, as well as the coatings on structural materials and aircrafts. And more specific to all of us, the things that we use to make ourselves beautiful every day. All of these things come from industrial chemical building blocks that are produced on the gigaton every day. But the way that these things are made is not very efficient from an environmental standpoint. Lots of times we require a huge amount of raw materials, and we're compressing it into maybe a tiny amount of actual usable product. Oftentimes, too, we're drawing a lot of energy off the grid, and this can have a huge carbon footprint in the surrounding environment. More specifically, at the end of these processes, we're left with a ton of chemical waste, and oftentimes it has to be treated very harshly so that we can safely discharge it to the surrounding environment. And more specific to all of us, a lot of these chemical processes result in a lot of pollution. Again, things that aren't really good for a surrounding community. Lots of time, chemical engineers, like myself, will be working on ways to improve these processes. And one way that's commonly used in about 94% of all industrial chemical processes is an additive called a catalyst. A catalyst can help make these processes more efficient. And specifically, it helps to cut down on the energy input and the waste output. So as we've heard Lisa and Rachel touch on earlier today, catalysts are these advanced materials that can accelerate chemical reactions. And how they work is by lowering the energy requirement necessary to get that reaction started. They essentially provide a platform for the molecules and atoms to interact and rearrange themselves to react together. Unfortunately, though, much like people, catalysts don't always behave the way that we want them to. Say we have raw material A, and we're trying to turn it into our desired chemical B, that we're going to turn into things like toothpastes and laundry detergents. Well, it'd be great if we could turn all of our A into B, and unfortunately, maybe by itself, A to B is quite a slow transformation. So, woody chemical engineers like myself might want to add in a catalyst. But all of a sudden, if it's a misbehaving catalyst, we might be making some unwanted chemical side product C. And potentially, B and C could together react to form D. Now, C could potentially be a potent carcinogen, and D itself a deadly pollutant. Neither of these things we'd want even in trace amounts, especially near something like B that we'd be putting into things that we'd buy off the shelves at the grocery store. So a lot of times we're asking ourselves as chemical engineers, how do we make the transformation of A only to B and shut off any chance of making C or D? And a lot of times this comes down very specifically to how that catalyst is designed in the first place. If we can, say, precisely architect a platform for these molecules to interact on, we could potentially shut off the side pathways to C and D and make only B. Turn 100% of A into B, get exactly what we want. And this is why people like myself are researching very hard to understand the rational design of catalytic materials. It's not only critical to making these chemical processes more efficient, but it's very critical to our consumer safety, so that we avoid things like potent carcinogens and deadly pollutants, even in their tiniest amounts. So let's dive into this a little bit more. Catalysts themselves oftentimes take the shape of metal particles sitting on the surface of a very rigid material. Industrial catalysts themselves historically have been quite ill-defined. A lot of times, say we're even just dealing with one metal, say titanium metal, for example. On an industrial catalyst, titanium metal might take the shape of many different surface structures, very different sizes, everything from individual titanium atoms to large nanometer-sized chunks of the metal just sitting on the surface. And from a chemical perspective, it's very hard to understand. Is it the titanium atom that's participating in the reaction, or is that large chunk what's responsible for what we're seeing at the end of our chemical reaction? A way to consider this perhaps a bit more is looking at these industrial catalysts as an everything bagel. Much like what we would consider to be different toppings giving different flavors, think of these different toppings representing different sizes of the same metal on the surface. So, if we were to span sort of a range of different sizes of surface species, we could consider everything from individual atoms, or a poppy seed bagel, all the way up to very, very large chunks of metal sitting on the surface, something like, say, a cinnamon raisin bagel. And what we'd like to understand is why do each of these behave differently? Now, for specific sets of chemical reactions, a lot of researchers have shown over the years that the more highly dispersed you get, so say the more poppy seed-like your metal clusters are, the more selective that chemistry is. Unfortunately, this comes at the trade-off of these materials being extremely difficult to make from a chemical synthesis standpoint. In contrast, if you had, say, very large chunks of metal, these catalysts are quite easy to make. And this is because metal atoms like to interact with each other and cluster. So while these are easy to make, historically, they're shown to be less selective to the things that we want to make. Industrial catalysts sort of smear across the spectrum. They have everything from the individual poppy seeds to the very large chunks. And so, what this has resulted in is historically quite inefficient processes at an industrial level. Though these catalysts, again, are somewhat easy to make, they're very difficult to understand from a fundamental perspective. My work as a graduate student is to make very precise poppy seed bagels to understand these everything bagels. Or in terms of chemistry, making site-isolated atomic structures at the surface of a rigid particle to understand how those surface species interact and behave in different chemical reactions. So more specifically, I make very precisely structured metal organic complexes. And to do so, I basically attach a bulky protecting group to an individual metal atom. And this bulky protecting group prevents these metal atoms from interacting with each other. Again, if we consider one metal at a time, this approach is actually quite generalizable and allows us to span the periodic table, making structurally analogous metals metal complexes for each of these different periodic family neighbors. So again, the approach is make this well-defined pre-catalyst, put it in a solution, add a blank particle, and what I get out of it is this very precise structure attaching itself to the surface that prevents the metal atoms from interacting with each other. A very simple heat treatment going to leave behind isolated metal atoms. This would be, to follow that analogy further, the poppy seed bagel that is very hard to make, but easy to understand from a chemistry perspective. My work seeks to explain the fundamental catalytic reactivity of those site-isolated materials so that we can better understand the way that those industrial catalysts are working on a gigaton scale. Again, not only does this help us explain existing catalysts, we now have design criteria for next generation chemical systems. If we can understand how those isolated atoms work, we can provide very nice, cogent design criteria for the perfect catalyst for any number of applications, hopefully shutting off for good any chance of making an unwanted chemical byproduct like a toxin or a deadly pollutant. All of these things can ultimately help these processes be more sustainable and green on a much larger scale. But specifically for you as the consumer, and me, the people who are buying these things off of the shelves, if we are able to consume less energy in an industrial chemical process, this means lower prices for us, as well as less pollution. Again, less chemical waste is perhaps a more direct impact on these surrounding communities because we're not risking anything dangerous getting into our air and our drinking water. And even further, we're guaranteed as a consumer, if we can make these chemicals more precise and more pure in the first place without requiring those very difficult separations, we're going to be able to assure safety and quality in anything that we buy off the shelf. In particular, catalysis is known to be a very powerful tool for making these reactions more efficient and faster. And my research aims to expand this and explain industrial catalysts a lot better so that we can make these processes more efficient on a very large scale. Thank you.